Hello, Marvelous Algebra 1 students. Welcome to your last day, not of Topic 4, we have a couple lessons left here, but your last day of solving systems of equations. We're going to focus on two things today. First, we're going to learn a few more tricks to help you with elimination. And then second, we're also going to focus on how to know when to use each method. And when I say method, we need to remember that there are three ways we learn this year to solve systems of equations. The first way is by graphing. That tends to be the least common. It's a little obnoxious to actually have to, come out here and say, okay, I want to solve this problem, so I'm going to go through and, make an X and Y axis and make sure my tick marks are accurate and make sure they cross in the right spot. So we tend not to graph too often, but there are going to be a couple questions on your test that are purposely set up so that graphing is the most efficient method. So you do still need to know it. But today what we're going to look at is how do we know when we use substitution versus elimination. Now, full disclosure, you can always use substitution and you can always use elimination. You never have to actually pick one over the other for each problem. However, some problems, especially on your test, are going to be designed so elimination is more efficient and some for substitution. And so we're going to discuss a bunch today about how you know when to do each method. So what we're going to start with are three problems down below. We're not going to touch graphing at all today, and your job is to decide which method, substitution versus elimination, do you think you would use for each of these problems, right? So you're going to go through where it says method, and you're just going to write the name for each one, and then you're going to explain quickly why. And then I'd just like you to show the first step. Now, when I say the first step, what I really mean is how do you combine these together to get a single equation? Because that's really what you do for both substitution and elimination. Somehow you combine these together and make one equation. So go ahead and get started. You don't have to fully solve. And then once you've looked at all three, go ahead and unpause and we'll see what we can do. All right, so for substitution, hopefully you remember that the key giveaway for substitution is usually that there's a variable by itself, or the variable is easy to get by itself. And here we might notice that y is equal to 5x minus 5. So as soon as I see that, I am absolutely thinking substitution. Because y is isolated. Maybe I should say because a variable is isolated. It doesn't have to be y, but in this case, y is the one that's isolated. And then, how do we get this into a single equation? Well, remember for substitution, we take the other equation first, 2x, and I'm going to write this twice, plus 3y equals 2, and then we are going to replace the variable that's isolated from the other equation. So I'm going to replace this y with 5x minus 5. And so we can see the equation we need to solve is 2x plus 3 times 5x minus 5 equals 2. I'm going to get rid of this just so we don't get confused. Now we're down to a single equation that you would solve for x, back substitute, and find your y. Looking at this second one, I'm inclined to probably not do substitution right away, though I'm actually going to show you a way to use substitution, which is pretty cool here. The reason I'm thinking not substitution, at least the way that we've learned it, is you would have to isolate y or isolate x. And when you go through to isolate y, you'd have to divide everything by 2. Dividing everything by 2 is going to give you 3 over 2, 3 over 2. That's going to be a gross decimal. Not that gross, 1.5. But I try to avoid decimals when I can. If you wanted to get x alone over here, you would have to go through and divide everything by 3. And 5 divided by 3 also doesn't come out nicely. So I think isolating here would be a little tricky. So what I'm probably going to try is elimination. However, I am going to go back and show you a way to do substitution here. With elimination, I'd say because maybe we'll say it's tricky to, kind of looks like an F, huh? It's tricky to isolate a variable. All right, so how do we get this into a single equation? Well, the first thing I might notice is that the x's and y's aren't lining up here. So what I'm probably going to do is take this 3x and I'm going to subtract it over to the left side. That's going to get my 3x's in line over here. And then, because I have the y's on the other side, I'm going to subtract 2y from each side so that my y's can line up. So what we have then, and actually I guess I could do this down below, is we have the top equation which didn't change at all. And then we have the bottom equation which now has a negative 3x on the left side, courtesy of algebra, and a negative 2y on the right side. Once we're here, just a nice reminder of elimination, we want to combine like terms on each side. On the left side, when you combine 3 and negative 3, it makes 0. They cancel. But it's really weird to see an equal sign with nothing on the left side. So if that ever occurs, you do want to write just a 0. You don't need to put the x's or the variables, just there's nothing there, so we put a 0. On the right side, 5 minus 2 gets you 3. Negative 9 plus 3 gets you negative 6. Now we're down to a single equation, which you should be able to solve. Now, I also promised you substitution here, and this is just a quick side note. It's not something that's necessarily expected of you this year, but it is pretty cool, I think. I noticed up here that 3x is equal to 5y minus 9. And what that tells me is if you see a 3x anywhere, what can you replace it with? Oh, 5x minus 9. So what we can actually do in this second equation is we can keep the 2y and keep the plus 3 at the end, but I'm actually going to replace the 3x with 5y minus 9. And now you can finish solving for y there. So this problem is doable by substitution, but that's kind of an advanced substitution move that we really don't talk about too much this year. Usually for substitution, we like a variable to be isolated. However, if the full term does match something, you can replace that if you'd like. All right, let's jump on to our last one. Okay, last one. I definitely don't want to isolate a variable here. None of that looks fun. So I'm thinking elimination, and looking at elimination, my x's line up, my y's line up, my equals line up, so elimination seems right. But then, when you try to combine like terms, right, this negative 3 and positive 5 will make positive 2, 7 minus 10, negative 3, 8 minus 10, negative 2. Now that is one single equation, but there's an issue with this equation. My equation still has 2 different variables in it, and that's a no-no. So we need something to actually eliminate here. So I am still thinking elimination, but the issue that we're running into is nothing actually cancels out. Nothing becomes 0. Even if we use the trick from last class where we multiply the top by negative 1, I don't think that's going to cancel, because what cancels a positive 5? Oh yeah, a negative 5, and that's not a negative 5. What cancels a positive 7? A negative 7. And so I think we're kind of at an impasse here, something we can't cross, or we can't get through. And so I'm just going to put a question mark on both of these, because we don't really know how to do this. So there are really 2 questions that come up. Question 1 is, can we do this using elimination? And question 2 is, if not, is there a different method? We're going to answer that second question first. There are other methods to solve systems. We don't cover them this year. So back to question 1, can we do this using elimination? Yes, we can. We just need to learn 1 or 2 other little tricks, and then we'll be fine. So problem 3 from the opener wasn't very pretty because nothing eliminated. So what we're going to do first is somewhat similar to what we did last class. We're going to look at 4 equations and see if we can find the value of x for each equation. And then we're going to prove that our value of x is actually the solution. So for example, on this first one, what plus 3 equals 5? Well, hopefully you said 2 plus 3 equals 5. And your proof is if you replace the x with the 2, then 2 plus 3 is equal to 5. So go ahead, take 30 seconds or so, try B, C, and D, and then we'll come back together. Well, as you went through, hopefully you discovered, somewhat similar to last class, that the answer is the same every time. Right? We knew the answer from A to B was the same because of what we learned last class. You might notice that if you compare this equation to the equation on B, you just multiplied every number by negative 1. That's why we got negative x, negative 3, negative 5. And so, what we learned last class is that if you multiply by a constant, by negative 1 at least, it does not change the answer. And to see that, because some of my students were stumped here, they're like, wait, shouldn't it be negative? Don't forget that there's a negative built into the problem. So when you replace x with 2, there is still the negative that's out front, and so it becomes negative 2 minus 3, which does equal negative 5. In fact, if we look down below for connections, equation B is equation A, just multiplied by the constant -1. And that might get you to start considering that there could be a connection between A and the other problems as well. If you look at C, I bet many of you found that the answer was 2, and you could have done 2 times that x value plus 6. 2 times 2 is 4, plus 6 more is 10. And then, if we start to look for that pattern, if we take the original equation and we jump over to C, can you see, pun intended, what we multiplied everything by to get over to our new equation? Yeah, we multiplied everything by 2 here. And what we noticed, hopefully, is that when you multiplied by 2, the answer also didn't change. Let's look at one more. The last one, well, it looks like if we're again looking for those connections, that we multiplied everything by 10 this time, didn't we? 10x, 30, and 50? Yeah, and x still ends up being 2 here. And so what we might conclude is that if you multiply, and don't forget that multiplication and division essentially do the same thing, right? If you multiply by 1/2, it's the same as dividing by 2. So actually, if you multiply or divide an equation by a constant, and I use this word constant several times. Constant is just a fancy way to say a number, like 10, or 2, or -1. It's a constant, it doesn't change. That's different than a variable, which is a letter, which can take on different values. Okay? If you multiply by a constant, it does not change the value of the equation. And that's really important for elimination. So let's go ahead and look at 2 examples on the next page and then get some practice in. So, first problem. If we look at this system, we should notice that the x's, y's, and equals are all lined up. So, elimination seems like a good way to go. But unfortunately, when you combine like terms, this makes 5x, this makes 9y, nothing made 0. So we don't want to eliminate yet. However, we want to ask ourselves, is there a way to change one equation so it will eliminate something in the other equation? For example, what would eliminate a -3? Oh, if this guy was a positive 3x. Unfortunately, using multiplication or division, like on the previous page, it's kind of difficult to change 8 to a 3. Right? It's not going to be a nice number that you divide by, so let's not change those. However, what could we eliminate 6y with? Well, you could eliminate 6y if this guy up here became a -6y. And I think, if you remember your multiplication, it's not going to be too hard to change that 3 into a -6. So let's show what we're doing one more step. I'm not going to change the bottom equation at all. I do, however, want to change the top. I want to make sure that this 3y becomes a -6y. Now, in order to make it a -6y, we're going to go through and use multiplication, because we know if we multiply by any number we want, it will still keep the equation the same. It'll look different, but it has the same value. So what do we need to multiply 3y by to make it into -6? Well, we need to multiply by -2. Now notice I grouped the whole left side in parentheses, and I'm doing the same thing with the whole right side. We want to do that because we need to show we're multiplying every number by -2. So -2 times -3 is positive 6x. -2 times 3y is -6y, and -2 times -21 is positive 42. Now we ask ourselves that same question again. Our x's are lined, y's are lined, equals are lined. Will something cancel out? And the answer is yes, the y's will cancel this time. So, as an explanation for our work, we multiplied the top equation by -2, so the y terms will cancel. Okay, let's finish solving this problem, though. I think you guys can probably tackle this part no problem, right? 6 and 8 makes 14x, -6 and 6 makes 0, 42 minus 14 gets us 28. So the new equation we're trying to solve is 14x equals 28. If we solve for x, we divide by 14 on both sides, and that gives us x equals 2. Are we done? Well, no, we know this at this point. We found part of the answer, x is 2. We're trying to find the point where the two lines cross. I only found half of the point. To find the other half of the point, we need an equation that will turn x's into y's, which means the equation needs to have both an x and a y in it. And we actually have a bunch of those up top. My students will say, well, wait, do we have to use the new ones, or can we use the old ones? Well, remember, if we multiply by a constant, it doesn't change the value. So all the new equations will do the same thing as the old ones. I usually prefer to use one of the original ones, and that's because they tend to have smaller numbers if you multiply, but it's up to you. So I'll just go ahead and choose this top one right here. Negative 3x plus 3y equals negative 21. All right, and then I think we just need to substitute. Negative 3 times the x value that we found, and that x value that we found was 2. This is again known as back substitution. We went back to an original problem and substituted in our new knowledge. And now we isolate y. 2 numbers attached to y, 3 is multiplying, 6 is subtracting, so let's undo the subtraction first. That gives us 3y equals negative 15. Finishing this off, we find that y equals negative 5. So what was new about this problem? What was new is that originally if we used elimination from last class, nothing would have eliminated and we would have gotten stuck. We used our new knowledge though to multiply an equation by a number. You could have also divided, by the way. You could have divided everything here by negative 2. That would have turned this into a negative 3y, and that would have been okay as well. I find people prefer to multiply those, so I stuck with that. And then we did elimination like normal. So let's look at our last example over here. X's, y's, and equals all lined up. Lovely. Now think about what we'd need to cancel each term. To cancel a positive 7, this would have to become a negative 7. Not easy to multiply to get there. To cancel a negative 10, this would have to become a positive 10. Also not easy for multiplication. This would have to become a negative 5y to cancel the 5y. And this would have to become a negative 2y to cancel the 2y. And unfortunately, none of these are super easy to multiply a single equation by a number, a constant, and get them to cancel. Well, what I'd ask you to think is about common denominators for fractions, right? Let's say, and just using some numbers here, let's say I wanted you to add together 1/2 and 1/5, and I got those numbers from here. How would you add those together? Well, you'd make common denominators. There is a way to make these two numbers into the same number. It's just going to be a larger number than both of them, right? To turn 5 and 2 into the same number, we need to find what's known as a common denominator. Sometimes we call this a common multiple. The smallest one is the least common multiple. And so I think 5 and 2 both go into 10. And so you could multiply by the other one to make them the same. So let's see what happens over here. I'm going to make 5y and 2y into the same value. And I'll start with the top one. I'm going to multiply the top by 5. We'll kind of do it one piece at a time here. So the top, when we distribute that 5, is going to become 35x plus 10y equals, let's see, 5 times 6 is 30, carry the 3, 5 times 2 is 10, plus 3 more is 13. Now, I don't just want to write this equation underneath, because currently this is a 5y and that's a 10. They won't cancel. And I also do not want to go through and multiply this equation by 2. If you multiply by 2, and hold off because I'm going to erase this, 2 times 5y is 10y. Those do not cancel. 10 plus 10 more is 20. So what do we need to cancel? Well, this needs to be a negative. And so we end up having to multiply the bottom by negative 2. This will give me negative 2 times negative 10x is positive 20x. Negative 2 times positive 5 is negative 10y. Negative 2 times 10 is negative 20. And now we have the x's, the y's, and the equals lined up, and our y's will cancel. So let's explain our work. We changed 2y and 5y into 10y and negative 10y. To change 2y, we had to do 2y times 5. And to change 5y, we had to do 5y times negative 2. Okay, so let's go ahead and finish solving. I would hope that you guys can do this one pretty quickly. Just showing you though. Cancel 35, and this is a positive 20, so we have to add 35 and 20 makes 55x's. 130 minus 20 is 110. So my new equation, 55x equals 110. Let's finish solving this. We need to go through and divide both sides by 55, and we find that x is 2. We're not quite done though. We know that now that x is 2, but we don't have the y. Okay, to find our y, we need to back substitute, so let's go back and find an equation. Any of them will work. Again, I like the ones with the smaller numbers. I'm going to tackle this one. Negative 10x plus 5y equals 10. Negative 10x plus 5y equals 10. Okay, and we found the x value in this case. So I'm going to go ahead and replace my x with 2. That gives us negative 20 plus 5y equals 10. Two numbers attached to y. 5 is multiplying, 20 is subtracting. So I'm going to go through and add 20 to each side. This gives us 5y equals 30. And then you say 5 times what is 30, or another way to phrase that is if you do 30 divided by 5, what do you find? Well, 30 divided by 5 is 6. I will also tell you, just from years of experience of doing this, this method is the one that I find students make the most mistakes on. Not because they're bad at it, but just sometimes they have sloppy handwriting. Sometimes they move too fast, but what they end up doing is they usually miss a negative or a positive sign, right? You're looking at so many equations that, and after you multiply, you might have forgotten that this was a negative here, and you might have screwed up the multiplication. And the frustrating part of this process is if you miss one negative sign or one number, it throws off the whole rest of the problem. Now, we make sure to grade so that if you just miss one negative sign, you don't lose the points for the entire problem. But my suggestion is, if you're getting stuck, have somebody else, a peer or a teacher, proofread your work to make sure you wrote both equations correctly, you have all the signs correct. The rest of it, I think you'll be all right on. So, we have 2 pages left to cover, and this is all in-class practice. Part 1 asks you to solve 2 equations that are in word problem form. Part 2 doesn't want you to solve it all, they just want you to set up and explain which one you do, just like the opener. And then Part 3 does want you to solve. Okay, so go ahead and try those. If and or when you get stuck, unpause, and I'm happy to take you through it. Alright, these first 2 word problems are pretty tricky. They're really kind of at the pinnacle or the height, or they're maybe the conclusion of our word problem explorations from the last couple lessons. If you might remember, we spent a couple days just setting up problems. We really didn't have too many to solve. Well, that's changing here. There is a problem like this on your test and on your final. They're going to give you a word problem and ask for the answer. And what they're not telling you is that you need to write a system of equations first, then solve it to find the answer. So let's go ahead and get to this. First problem is very similar to one we did recently where they give you different types of coins. So hopefully writing this equation is somewhat familiar. There are 12 coins in my bag that consist of quarters and dimes. Well, that actually already gives us one equation. We know some number of quarters plus some number of dimes has to add up to equal 12. We also know that the value of these coins is $2.25. And if you remember, this is the trickier equation here, right? We don't just want to say quarters plus dimes equals $2.25. We don't want to do that because this is the number of quarters. In order to add the quarters and dimes to equal $2.25, we need to convert them to actual dollar amounts. The way you convert a quarter to a dollar amount is you take it and multiply by 0.25. right? If you had 4 quarters and you multiply by 0.25, you'll get $1. Same thing for dimes, we need to multiply by 0.10. Once we have these two equations, then we have to think about how would we solve this. That's really where that choosing method comes in. This one does suggest to try to solve problem 1 with elimination and problem 2 with substitution, and so I'm going to stick with that. It is very possible to solve this problem with substitution. You could subtract q to the other side and then use substitution from there. But since q, d, and 12 are all lined up, I think that this one might be a pretty quick way to practice what we learned earlier today. And the question we'd ask ourselves is, what would cancel out 0.25q? Well, and I think the thing that would cancel out a 0.25q is if this was a negative 0.25q up above. Okay, it's currently not, so I think we're going to have to go through and multiply both sides by negative 0.25. Right? So I'm going to rewrite this system of equations down below so we can keep track of what's happening. This will give us a negative 0.25q minus 0.25 times d equals, and let's see, 0.5, that's a quarter of 12. Let's see, I think a quarter of 12 is going to give us negative 3. And then the bottom equation hasn't changed at all. But now I'm just going to be a little bit more careful about lining up my variables here. We'll see what we can come up with. Okay, well, if we combine like terms here, is anything going to cancel? Well, I think so. We have these two, we have our equals, cancels. Then we have negative 0.5 plus 0.1, and I think that's going to give us, negative 0.15, I think d. And then if we put these together, I think this one will give us negative 0.75. All right. Well, to finish this off then, we want to solve this equation by dividing by negative 0.5 on each side. And that tells us that our number of dimes, and you'll probably want a calculator for this one, or you could just start adding up 15s till you get to 75, will be 5. So we have 5 dimes. Now, you might be groaning and you're like, oh, we have 5 dimes, now we have to do that back substitution thing. Well, you do, but don't get lost in the math. Right, this top equation is just telling you you have 12 coins. If you know you have 5 dimes, can you do the math in your head? 5 dimes, how many quarters? Hopefully you said 7 quarters. And that's because 5 plus 7 has to equal 12. So you could substitute the 5 in here or over here, but I think it's probably going to be faster if you just bring some logic in and realize you have 5 dimes and 7 quarters. All right, let's look at our second problem. 2 different electrical businesses charge different rates. Business A charges $30 for a service call plus an additional $45 an hour per labor. Business B charges $45 for a service call plus an additional $40 an hour for labor. A couple of things we should realize before we start here. A service call is the price that a company charges just to come out to your house. Right? So if you're like, I want you out here, they're going to come out regardless. That way they're kind of covering costs in case there's actually nothing wrong. They're like, well, my time is valuable. I need to at least spend a little bit of money, or you have to pay me a bit, so on and so forth. So the service charge only happens once. I will also tell you, though, if these are electricians that are coming out, $45 an hour for labor or $40 an hour for labor is way cheap. I bet most electricians would charge between $50 and $100, if not more, per hour. It's a good trade to go into. All right, so let's get this done. First thing we need, of course, are our system of equations, and let's start with business A. $30 only happens once, plus an additional $45 times the number of hours that business A is working. We're not done yet, though, because that's not an equation. An equation has an equal sign, so we have to ask, when you have some number of hours, let's say that they're there for 5 hours, and you do all this math, what is the answer telling you? Well, it's telling you, I think, your total cost. So you could use T or C or something like that. Because this one isn't as obvious, I'm going to define my variable. H is the number of hours worked, and C is going to be the total cost. All right, let's look at our second one. Second one I should do in green. $45 per service call, but less money per hour. After how many hours would they charge the same? And that's actually pretty important, right? Because initially you might say, well, this one's pretty cool because you only have to pay 30 bucks even though you pay a little bit more. So I think the purple one will definitely be charging less at the beginning. However, that additional $45 versus $40 eventually is going to add up. And so you want to make sure you're like, well, if it doesn't really matter, or if you know it's going to be some number of hours, you want to know which one you should call. So here we go. In order to do that, you could use elimination. To do elimination on this, I would probably multiply the top by -1, and then those C's would cancel out. However, we also want to remember that substitution is a viable method, and for substitution, we need a variable by itself. I think C is certainly by itself here. So what does that mean? Well, it means we take the second equation, the one we didn't do anything with, and we are going to replace C with what's in the first equation, 30 plus 45 times h. Once we're here, we have a single equation with only one variable. Let's go ahead and solve. First thing I always like to do is notice that the h's are on two different sides, so we need to bring them to the same side. You could subtract either one. I chose 40 though because I noticed that 45 minus 40 is going to give us just 5 h's. Not bad at all. This one just has 45 left. Now we have the h's on a single side, and so we need to isolate. Okay. How do we undo adding 30 and multiplying by 5? Well, the first thing is we subtract the 30 from each side. Okay. That gives me 45 equals 5h. And there you can just ask yourself the question, 5 times what is 45? Or you can go through and actually solve. And if you actually solve here, oops, I made a mistake. Hopefully you noticed that. 45 minus 30 is 15. Whoopsies, I guess I'm tired today. Second try. 5 times what is 15? Well, 5 times 3 is 15. Therefore, after 3 hours, the price is the same. What is the price? Well, that's our back substitution piece. To find the actual price, I'll just use this purple one up here. 30 plus 45 times the 3 that we found will be the total cost. Okay, that gives us 30 plus, let's see, 45, 90, 135. And so that tells us our total cost will be $165. So if you're looking to hire one of these two companies and you know they're going to be out for 3 hours, then it doesn't matter which one you hire. If it's less than 3 hours, do the one that you initially pay less for. If it's more than 3 hours, then business B is actually going to end up being the cheaper. Okay, let's move on to part 2. Not actually solving here, just setting these up. First problem, let's see. X's, Y's, equals, they are all lined up. I think maybe elimination will be pretty quick here. You could also, of course, subtract your 2x over to the other side. There's nothing like that. I'm just taking a quick peek over here and seeing if there's any others that we might want to do. Sure. Okay, so yeah, let's practice some elimination. That was kind of our new stuff today anyways. Substitution is totally fine if you'd like to do it that way. For elimination, I am noticing that you could cancel out 4 by making this -4, or you could cancel out 3 by making this -3. I'll cancel out the x's though. So I'm going to go through and multiply the bottom by -2, and that's going to match my 4 up above. So this is going to become top equation, not changed at all, but the bottom equation will be -4x, don't forget to distribute to both, minus 2y equals +4. And to make that single equation, now we combine like terms. These cancel. This is 1y, which is just y, and 0 and 4 makes 4. And actually, making a single equation already solved for y. That was pretty nice. We don't have to find x here. If you wanted to, you could back substitute. Let's try another. Variable's already isolated on this one. Substitution for sure. I'm not even going to consider the other options, even though elimination is fine. Substitution, we're doing it. 2, we're going to replace x with what x is equal to, 6 minus 4y. Nice. That's something you should be able to solve if you distribute, combine like terms, all that fun stuff. Next one. Let's see here. Well, I don't think anything's too easy to get by itself, but I am noticing a +2 and a -2. So I think we can make that work with the elimination. Whenever you have those opposite signs, elimination is a good way to go. The first thing I'm going to do, though, is I'm going to switch the sides of the equal sign. I'm going to put the 2y on the left side, leave a bit of a gap, and then put the 3x plus 7 on the right. So I just switched the two sides of this top equation. And then my bottom equation, I'm not changing at all. The bottom equation is still negative 2y minus 1 equals 10x. Once we're here, we ask ourselves, are the x's, the y's, and the equals all lined up? And yeah, they are. You'll notice there's a 7 on the right and a negative 1 on the left. If you wanted, you could add the 1 to the right, but you don't have to. You can just go through and combine your like terms right here. 2y and minus 2y cancels, leaves us with negative 1. 3x and 10x makes 13x, and then the 7 has nothing to combine with, so it just stays. And from there, you can solve if you'd like. All right. This guy, oh, I bet I can use my cool substitution trick here. Right? This is one that I briefly mentioned on the opener, and I think it's something cool to keep in mind. Notice that we have 3y isolated, and there's a 3y in the top equation. So 4x plus, and instead of 3y, I'm going to replace it with negative 5x plus 1, because 3y is equal to negative 5x plus 1. Now we have a single equation. You can put the invisible 1 here, distribute, and solve. X's, y's, equals all lined up. This looks like elimination. You could cancel out the 4x by making this a negative 4, but you could also cancel out the positive y by making this a negative y. So I think I'll tackle that one. I'm going to go through and multiply both sides by a negative 1 here. This is going to be elimination. And let's see what we get. The top equation has not changed. 4x plus y equals negative 10. The bottom equation becomes negative 1x minus 1y equals positive 14. And now let's see what cancels. 4x minus 1x is 3x. 1y minus 1y is 0. Negative 10 plus 14 is 4. 1 to go. X plus 3y equals 1, negative 5x plus 4y equals negative 24. You could substitute by subtracting this over. However, to me it looks like it'd be really easy to make this x match the negative 5x. And to do that, I'm just going to multiply by positive 5. Okay, so again, I'll use elimination. Everything's all lined up and ready to go. And this gives us 5x plus 15y, don't forget to distribute, equals 5. Bottom equation remains the same. And combine like terms. 0, 19y equals negative 19. All right, well, this is going to move us on to the last page here. This last page are just a bunch of practice problems, and some of them are pretty easy. Some of them are a little bit trickier, and you're definitely going to want to go through and try them. I think I made them all come out to nice numbers, but as I work through, we'll see if I made any mistakes. I will tell you that the top 3 problems are pretty darn straightforward. The next 3 problems are a little bit trickier. The next really 6, the last 6, are mostly designed for elimination. I think these next 3 you're going to have to multiply by a single number. And then these last 3, I think you're going to have to multiply by at least 2 different numbers on these guys, and this last one is a special case. So, good luck with these 9, substitution, elimination. See if you can use substitution at least 3 times. However, if you can't do it and you're like, yeah, it doesn't work out, and honestly looking at this, I'd probably only use substitution maybe twice. Give it your best shot either way. Make sure you can get the answer. We're getting the full x and y whenever you're done, or if you get stuck, unpause, and we'll go through it together. Alright, this first problem certainly looks like substitution to me. I see y by itself, so let's tackle it. We're going to go through negative x plus 2. Don't forget to leave that 2 in there. And we're going to replace y with 31 minus 8x. This gives us negative 1x. We need to distribute. So that's plus 62 minus 16x equals negative 6. Combine some like terms. I see negative 1x minus 16 more is negative 17x's plus 62 equals negative 6. And then I should have written smaller, but that's all right. We're going to subtract 62 from each side. This will give me 17x equals negative, looks like 68. And we finish by dividing both sides by 17. You can have your calculator ready, or you can guess. To me, if it's going to end in an 8, I bet it's going to be 4. And indeed, if you work it out on your calculator, I think 4 times 17 is 68. So we found the x value for the answer. I'll leave the answer down here. We still, however, need the y. And I think the y is going to be back substitution. But the nice part is with substitution, it's very easy. We know that y is equal to 31 minus 8x. So let's substitute in the x value that we just found, which is negative 4. And so we end up with 31 plus 32. And so the y value is actually very large here at 63. Next up, this one looks like straightforward elimination. I bet we could just go through and combine like terms as we move down. 0, 10x equals negative 40. Not bad at all, right? Divide by 10. And we find that x equals negative 4. Now, the nice part with elimination is usually the beginning is faster to find the first variable, but then for substitution, it's faster to find the second. I think we'll see the same thing here. So it doesn't matter which equation you pick. I'm going to pick the bottom one. It has slightly smaller numbers. 3 times x plus 4y equals negative 10. And we'll replace with the x that we found. This gives us negative 12 plus 4y equals negative 10. Right? And then we isolate our y. Add 12 to each side. 4y equals, and this one looks like 12 minus 10, which is 2. Finishing this off, we need to divide both sides by 4. And notice here that y actually equals a fraction. 4 doesn't go nicely into 2. If you split $2 amongst 4 friends, your friends don't get a whole dollar at all. They just get 2 over 4, or if you reduce, 1/2. Moving on through. Third problem seems like pretty straightforward substitution. We know what x is equal to, so we take the other equation and we go through and say negative 2x. Nope, we need to replace the x. Negative 2 times something equals 3y plus 33. And we replace the x with 6 plus 3y. From here we need to distribute. This gives us negative 12 minus 6y equals 3y plus 33. And sorry, you might hear my son in the background who's chuckling at me. From here, I would want to move all my y's to one side. I think to make them positive, I'll add 6y to each side. You could have also subtracted 3y. There's nothing wrong with that. Gives me negative 12 equals 9y plus 33. And then we go through and finish isolating y. Subtract that 33. This gives us negative 45 equals 9y. And to solve, we divide both sides by 9, which gives us y equals negative 5. Once we find the y values, we know that the y is negative 5. We need a little space. We'll use this over here. And we need to find the x. Luckily, we know the x equation is 6 plus 3y. And since we just found y, we can replace the y with negative 5. Looks to me like we get 6 minus 15. And that should bring us to negative 9. All right. These first 3, as mentioned before, should have been pretty straightforward. There were 2 substitution questions and 1 elimination. The rest of these are, for the most part, really going to be all elimination. The next 3, you're going to have to multiply by a single constant. And the last 3, you're going to have to multiply by 2 constants. So let's see what you guys can do. And then once you get there, unpause and I'll finish it off. All right, let's see what we can do with these last 6 problems. We'll go through them pretty quickly, and hopefully we'll see the patterns that occur. So, first problem. 9 and 18 make 27. Negative 4 plus 7 make positive 3. Uh-oh, neither of them add up to 0. This is what we covered earlier today. If neither of them add up to 0, we need to use one of our new elimination skills. Looking at these, I think 4 doesn't go nicely into 7. 7 doesn't go nicely into 4. However, 9 does go nicely into 18. 18 goes nicely into 9, but you'd have to divide by 2. And if you divide by 2 here, 7 divided by 2 isn't nice. So I think you find most people tend to multiply instead of divide. You can divide, though, and I'll try to find an example to show you maybe on the next one. So what I'm going to do is take this guy and think, how do we turn 9 into something that will cancel 18? And by the way, to cancel 18, we need a negative 18. Well, I think we can multiply both sides by negative 2 here. And this is going to give me a new system of equations, right? This is going to give me on top negative 18x, don't forget to distribute, plus 8y equals negative 52. On the bottom, 18x plus 7y equals 22. And then we're back to normal elimination because at this point, my x's will eliminate or cancel. 8 plus 7 makes 15y's, and negative 52 plus 22 is negative 30. We should probably finish solving this guy. Just divide both sides by 15. And that gives us y equals negative 2. Okay. Almost done, but recording this down here so I don't forget. Now that we know y, we need to find x. You can use any of these 4 equations. So this guy, this one, this guy, or this one. I tend to use one of the originals because I find they have smaller values, smaller numbers. I'm going to work this first equation down here. 9x minus 4, we know the y now. The y is negative 2. I also, by the way, find drawing arrows helps me make fewer mistakes when I go back up, because sometimes people say, oops, and they write the 22 or something like that. But the arrows help me. So 9x plus 8 equals 26. And let's finish solving. Subtract 8 from each side. 9x equals 18. And divide by 2. And by 2, I think I'm jumping the gun here. I really meant divide by 9, and 18 divided by 9 is 2. And we found our answer of 2 comma negative 2. Moving on. Next one's pretty darn similar. Notice we could turn 3 into a positive 6 by multiplying by 2. We could turn 2 into a positive 4 if you'd like as well. But I did promise you a division one, so let's work the other way. Let's turn negative 6 into something that would cancel positive 3. And I think I could do that by turning negative 6 into negative 3. Negative 6 turns into negative 3 by dividing by 2. Of course, if you divide one thing by 2, you need to divide every term by 2. What does this give us? Well, we have our system here. The top doesn't change at all. However, the denominator becomes negative 3x minus 2y equals negative 4. Well, this is weird. It looks like they are inverses of each other. I think everything here is going to become 0. However, there still is an equal sign. We can't just leave both sides blank, so we are going to put zeros on each side. What does that mean? What happened? Well, another way you could look at it is you could have thought about taking this equation and multiplying it by negative 2. If we multiply that top equation by negative 2, it becomes negative 6x minus 4y equals negative 8. And the bottom is negative 6x minus 4y equals negative 8. What should you notice about each of these equations? Oh yeah, they're the same. And if you have an xy axis and you graph two equations that are exactly the same, here is one line, here is the other line. Well, in how many places do those two lines intersect? They intersect everywhere, infinitely many solutions. Another way you can remember it is that using algebra, if all of the variable or variables cancel, and you are left with a true statement and 0 is equal to 0, then this means infinitely many solutions. And by the way, you do need to write out infinitely many solutions. You can't just stop with 0 equals 0. We don't know if you know what that means. You're like, 0 equals 0, the answer is 0. Well, no, not necessarily. All right, next one. Looking at this guy, I think we could either turn 4 into negative 16 or 16 into negative 4. Totally your choice here. I'm going to make these numbers smaller though. So I'll use that weird division trick. I'm going to divide everything here. Oops, no I'm not, because 10 divided by -4 isn't going to come out nicely. So instead, I think I will multiply the top equation. Let's multiply by -4. That'll get us a -16 here, and see what we come up with. Okay. I don't know why I'm doing that either. Second try. -16 plus 12y equals -64. 16x plus 10y equals 240. Combining our like terms, performing some elimination, we end up with 22y. Okay? And then on the other side, we have to do a little bit of math here, but hopefully it's nothing too terrible. We know it's going to be 100, of course. And then, let's see, to get 6 to a 4 is an 8, but we don't have to carry the 1, so I bet it's going to be a 7 and then 6. 6 and 4 makes 0, 7 and 6 is 13, 14. I think that looks pretty darn good. Then we have to go through and finish solving for y, so we need to divide both sides by 22. How does 22 make 6? Well, you can multiply by 3, and I think that would be too short. That would be 66, wouldn't it? So if we do 176 divided by 22, I just whipped out my calculator. Well, we get 8, because 2 times 8 is 16. That makes sense. So we have an answer of something, comma, 8. Looks lovely so far. We just have this last bit. We know y is 8. Let's take an original equation. I'll take this guy. Seems like it's a little bit easier. 4x minus 3 times whatever our y is 16. 3 times 8. We end up with 4x minus 24 equals 16. And then we start solving. Add 24 to each side. 4x is equal to 40. 4 times what is 40? Well, 4 times 10 is 40. And we have our answer. Now, those three you had to multiply one equation by a constant. These last three, you might have to multiply both equations by constants. This is kind of the end or the pinnacle or the height of our elimination tasks. So 3x plus 2y equals that, and 5x minus 9y equals that. I think turning 3 into 5 can be challenging. Same for 5 to 3, and 2 to 9, 9 to 2. So if there's not an easy number to multiply or divide one equation by, we're stuck with both equations. What do 3 and 5 both go into? What's a common multiple of 3 and 5? Well, hopefully you could think 3 times 5, 15. So we could turn both of those into 15s. Or, what do 2 and 9 both go into? 18, right? We could turn 2 and 9 into 18. It's totally your choice here. I noticed that one is negative, one is positive here. So what I'm going to go through and do is multiply this bottom equation by 2. And so what that's going to do with the bottom equation is give us 10x, doesn't matter, but minus 18y. That's the key one. 2 times 46 is 92. Then the top equation, I'm going to multiply by positive 9. So notice I was able to multiply by two positives here because they already had opposite signs. 9 times 3 is 27x plus 18y equals negative 18. Then we combine our like terms. Mix a 0. This gets you 37x equals a 92 minus 18, I think, is 74. To finish this off, we divide both sides by 37, and I'm pretty confident that 37 times 2 is 74. So we're part of the way to our answer. Our answer is 2 comma something. To find the something, move back to an original equation. You could use one of these as well, but those numbers are pretty big. I'm taking this one. It looks like it's the smallest numbers, and it's 3 times our x plus 2y equals negative 2. And our x was 2. So 6 plus 2y equals negative 2. And we solve. Subtract 6 from each side. 2y equals negative 8. And divide by 2. Y equals negative 4. And then there were 2. Okay. 3x minus 5y equals negative 16, and 2x minus 3y equals negative 8. I don't think these are easy to make into each other, nor these, so we're going to have to do that least common multiple. Think common denominators with fractions. What number do 3 and 2 both go into? They both go into 6. So let's go ahead and multiply our top equation by 2. Doing that, we will have 6x minus 10y equals negative 32. What will cancel out of 6x? Well, a negative 6 will cancel out of 6x, so we need to multiply through by negative 3. Negative 6x plus 9y equals 24. Okay, looking at this, negative 1y equals, and I think the difference here is probably negative 8. Yeah, negative 32 plus 24. Finishing this off, we should probably divide both sides by negative 1, and that gives us the answer of y equals 8. All right, let's go ahead and jump back to an original equation here. Take this bottom one. This gives us 2x minus 3 times whatever y is equals negative 8. 2x minus 24 equals negative 8. Add that 24 to each side. 2x equals, let's see, 24 minus 8 is 16. 2 times what equals 16? 2 times 8 equals 16. All right, we have 1 to go. 2x plus y equals 6. 2x plus y equals negative 7. Well, I'm already suspicious here. 2x plus y equals a constant and 2x plus y equals a constant. These equations look identical, but they're equal to different values. I'm pretty confident that these are going to be parallel lines. Not the same line because they equal a different answer, but parallel because all the variable stuffs are the same. However, let's see what happens if we multiply just the top by negative 1. And I'm choosing negative 1 because that's going to keep the bottom the same, and it's going to turn the top into exactly the same as the bottom, but with negatives, and of course negative 6 instead of 7. When you combine your like terms here, cancel, cancel. We can't leave the left side blank, so we put a 0. Negative 6 minus 7 is negative 13. There are no variables left. So what does that mean? Well, if you look at the graphs over here, and I prepared them for you, you'll notice that I was correct. We do have 2 parallel lines. And where do parallel lines cross? Oh, that's right, they don't. So these are 2 lines that don't cross. That means that there is no solution. And as a reminder, you do have to write no solution. You can't just stop here. How do you know it's no solution without the graphs? Well, if all the variables cancel and this is false, because I'm pretty certain that 0 is not equal to negative 13, then that's the giveaway for no solution. So hopefully you're feeling pretty confident on this elimination and a little bit of review for substitution for choosing a method. I appreciate you hanging in here. I know this video is a little bit longer, but we really did need that practice to be successful. This actually concludes our systems of equations section of topic 4. The last 2 videos are going to focus on systems of inequalities.